Hello everyone, welcome to the Electromechanical Devices course. In this video, we're gonna continue chapter 5. As a very quick summary of the thing that we already discussed in this chapter, we started with like a little bit discussion about the complex numbers. Then we introduced the phasors, and we knew how we can do some operations over the phasors. And we said that these phasors are the fundamental thing that we're gonna use in the method that we're gonna use or implement during this chapter, was it chapter 5. We said that the difference between the method that we're gonna use for this chapter and the previous method in chapter 4. In the chapter 4, we were working in the time domain, and as long as we were already working in the time domain, it is like kind of complicated thing as we discussed before, and because simply we're gonna end up with some differential equations, and we have to solve these differential equation. And solving differential equations in comparison to the simple algebraic equations, straightforward algebraic equation, it is much more complicated, and it would require some computational tools like the MATLAB software, for example, as we practice through chapter 4. And you could say that we can handle or we can do analysis for electrical circuits in the time domain as long as the electrical circuit is a simple one that include the three electrical elements, the capacitor, inductors, and the resistor in one electrical circuit. But this electrical circuit should be like only one single loop, and we can solve analytically, we can solve this equation or the circuit equation, the differential equation, if in case that there is just one equation, two equations at maximum. But in case that we have so many equations, we aren't going to be able to handle this type of problem, and that's why it is much more complicated. But we have to consider the electrical circuit in the time domain and we have to use the method that we explained in chapter 4 as long as we are interested in the transient behavior of the electrical circuit. But in chapter 5, and this is the objective of this video, is to give you another method that can be suitable for investigating or studying the steady-state behavior of the electrical circuit. And this method depends on converting the electrical circuit into another domain, which is known as the frequency domain. We found difficulties in solving the electrical circuit or doing analysis of the electrical circuit in the time domain, so we can figure out another approach which depends on forming phasors. Like your objective is just to convert all the components or the voltage and the current through the electrical circuit into phasor form. Once we do so, we automatically gonna convert the electrical circuit. It looks like we already converted the electrical circuit into another domain, which is commonly known as the frequency domain. And this is the objective of this method, that this method depends on converting the electrical circuit using the phasors concept into the frequency domain. When we convert the electrical circuit into the frequency domain, looks like we're already getting an equivalent electrical circuit with all the elements within the electrical circuits are resistors. We didn't face any difficulty through chapter 2 when we did analysis for resistive circuits. In case that would have resistor, no problem, because simply the circuit equations are linear algebraic equations that can be simply solved, no problem with that. But when we implementing or incorporating any capacitor or inductor, we shall end up with a differential equation as long as we're already working in the time domain. So that's why we had difficulties a little bit, and it was much more complicated through chapter 4. But we have to do so if we're already interested in the time resistance as a transient behavior of the electrical circuit, as I said. But here, since we are interested in the steady state, that is fine to convert the electrical circuit into an equivalent domain, which is the frequency domain. For this case, looks like you already replacing all the electrical element, the resistor, the capacitor, and the inductor, with an equivalent resistor. So we're going to end up with a resistive circuit, and we can apply the same method that we explained in chapter 2 on solving this electrical circuit. So this is the main outline or the main idea behind the method that we're going to use for this chapter or this part. And again, we can apply this method as long as we are interested in the steady state behavior. But if we are interested in the transient behavior, we have to apply the method that we covered in chapter 4. It means that we have to work in the time domain, not in the frequency domain. Make sense? So this is the basic idea of this method, and this method depends on forming impedances. So what is the impedance? Impedance, this is the equivalent resistance to the original electrical element. If you do have a capacitor, so we're gonna kind of converting this capacitor into another equivalent resistor. If we have inductor, we're gonna convert the inductor into another equivalent resistor. So this is the basic idea of the impedance. This converted thing, the converted inductor or the converted capacitor, we're gonna call it impedance. So this is the impedance form, or you could say that this is the conversion of the electrical circuit from the time domain to the frequency domain, depends on forming phasors and impedances. Phasors, these are the voltages and the current, because within any electrical circuit, we should have a volt and we should have a current roaming and rotating through the electrical circuit. And the current and the volt are two things that distinct, or two things that already change from one electrical element to another electrical element. So changing the electrical element itself from the time domain to the frequency domain, this is known as impedance. Like you already driving new impedance or an equivalent form of the original electrical element known as impedance. And the conversion of the current and the volt from the time domain to the frequency domain is known as phasor. Like you're already gonna convert these different variable time varying things into phasors. So using the phasor and the impedance concept, this is the basic idea or the method that we're gonna use in this chapter to convert the electrical circuit again from the time domain into the frequency domain. Before I explain to you the method, let us discuss what does it mean impedance. But let us give like a very quick review of the phasors that we already formed in the previous meeting. So we said that the phasor, generally speaking, that in case that would have a volt or a current within this sinusoidal form, and we said that the type of the form that we're gonna use all the time is the cosine form. Like it's gonna have cosine function, but this function is still the sinusoidal form. And this is the peak or the maximum value or the amplitude of this sinusoidal form or function of the volt V1, and this is the frequency of the volt, and this is the phase, and this is the time, right? This is the phase angle, and we do have another voltage of the same frequency. We said that the key idea that these two voltages or all the voltages that we can sum together, they should have the same common frequency, which is omega. So this omega is still the same, but this is a different peak or different amplitude and different phase. So if we decided to form or to convert the sinusoidal form into a phase form, we said that your objective is just to drop this omega t and drop the cosine, but make sure that this function should be cosine, this one also should be cosine, having the same omega t, the same omega d. Drop these two things and just use the peak, which is 3, and put the angle as 40 degrees. So this is the phasor form of the original sinusoidal form of V1. V2 also, the phasor form of V2 is going to be the 4, which is the peak, and the angle is going to be negative 20. So this is the phasors of the V1 and V2, the sinusoidal forms as already given. So this is the sinusoidal form, this is the representation. And if we decided to compare the relation between V1 and V2, so the relation, it depends mainly on the phase, this angle. Like this angle, this phase angle, it is 40, and this angle is 20. So if we decided to give like a schematic representation to these phase angles of the 40 and the 20, so V1, it should be at angle 40 degrees, rotating from the x-axis, from the real horizontal axis. Assume that this is the real axis, or like x-axis or y-axis, that this should be the real part axis and this should be the imaginary axis, or just x and y. So starting from the x-axis, rotating in the counterclockwise direction, as long as this angle is positive, you're gonna rotate counterclockwise direction to end up with the V1 vector, like you're already drawing a vector, because as we mentioned, the phasor is like a vector in the previous video. So how about V2? V2, it has a magnitude of 4. It means that the length of this line, it should be a little bit longer. This should be the length of this line is just 3, but this length is gonna be just 4. And the angle, it should be negative 20. It means that you're just gonna rotate in the clockwise direction. So if the angle is negative, we're gonna rotate clockwise direction starting from the positive x-axis. This is our main reference. So if we decided to do like a comparison between V1 and V2 in terms of the phase, so we're gonna say that these two statements are fine. This is one statement and this is another statement. Both are correct. If we said, for example, for this one, we're gonna say that V1 leads V2 by 60 degrees. Like this is like the difference. What should be the angle between this V1 and V2? It should be 60 degrees. But remember that our main positive reference, that our positive angle or our reference is the clockwise direction. If the angle rotates clockwise direction, it means that it is a positive angle. So if I said V1 leads V2 by 60 degrees, it means that like if we started from V2 and rotated 60 degree counterclockwise direction, in the counterclockwise direction, we're gonna find V1. It means that V1 is in the front of V2 and V2 is on the back, okay, or comes after V2. Like this is the first place and this is the second place, kind of. Or we can say that V2 lags the V1 by 60 degree. Lags, it means that it comes before, after the V1 by 60 degree. Lags here indicate that this is like you already rotating in the clockwise direction. So that's why lags indicate something negative, right? It comes after. It already comes late, kind of, with the 60 degrees. It means that V2, it comes behind or after V1 by 60 degrees. So this is how we can relate one phasor to another phasor in terms of the phase angle. We relate them mainly based on the phase angle, and this is gonna be clear in the sinusoidal wave. It means that, for example, if we started the two waves of these two waves or these two phasors, V1 and V2, working within a certain electrical circuit, and you could consider like you do have a reference line and you switch on the electrical current and the volt and V1 and V2. So you're gonna find that V1 will touch this reference first, then V2 will come after, and the difference will be dependent on the phase angle of 60 degree late. Make sense? So this is the physical meaning of V1 and V2 and how would be related. And this is like a quick revision how we can convert a sinusoidal form into a phasor form. Simply you're gonna pick the peak value and you're gonna use the phase and get rid of the cosine and the omega, but make sure that you have this form in the cosine form. Make sense? So now let us discuss the impedance. To explain the impedance, let us consider starting with the inductance. As I mentioned very quick on the top, impedance, it is like we already converting the inductor and the capacitor into an equivalent resistor. So let us start with the inductance or the inductor. Assume that you have a coil inductor with this form, and this coil it is, and in this coil there should be like a current I of t, L of t already passing through this coil. And this current function is already given as given here, like I or L of t. This is the current is given as Im. This is the peak value. This is the magnitude of the current. And the current function is given in the sine form as omega t plus theta. Where theta, this is the phase angle, this is the frequency, and this is the peak. We said that we have to convert it into the cosine form, right? So if we decided to convert this one into the cosine form, we can convert it into Im cosine omega t plus theta negative 90. You're just gonna add negative 90 here to convert into the cosine form. Make sense? Then if I ask you to find for this current, to find the voltage, VL of t, how much it is. So the voltage is gonna be L, the di by dt from chapter 3. This is how the voltage is related to the current over inductor, that the voltage equals, it is proportional to the time derivative, to the first derivative of the current, right? So this is the IL of t. So what is the derivative of this cosine or even the sine? You can work on the sine. Let us work on the sine form or the cosine. Both are equivalent, okay? So if we decided to work over the sine form, this is gonna give us the Im, which is the amplitude, and the cosine, the sine, it will be cosine, makes it, right? It's gonna be the cosine of the angle. Let us have a space like the cosine angle, the cosine times the derivative of the angle itself, which is plus theta, and we have to multiply times the derivative of this angle with respect to the time, because we're already converting with the time. This is gonna give us the omega. And definitely we're gonna have L, which is just constant, right? So this is the M omega cosine omega t plus theta. This is the derivative times L. This is gonna give us the the voltage function as already given. So as you can see, the voltage is already given in the cosine form, but in the current, it was given in the sine form, but we can convert it again into the cosine form. If I ask you to write both the current and the voltage, this is sinusoidal form and this is sinusoidal form. So how about if we decided to convert them into their equivalent phasor form? So the phasor the phasor of IL, it's gonna be the phasor of this one is gonna be the magnitude or the amplitude, and the angle, it should be theta negative 90 degree. Remember that you have to convert first to the cosine. Don't just put theta. If we consider the sine, we're gonna put theta here, but this is not the equivalent form. We have to stick to the cosine form as we agree. So this is the phasor form for the current, and the phasor form for the voltage is gonna be the volt, the magnitude of the volt. All of this term is just the magnitude, so it's gonna be the Im omega L. This is the magnitude, and definitely the angle is gonna be theta. So as you can see, there is a difference in the magnitude, and forget about the magnitude, but there is a difference in the angle. As you can see, one leads the other, and one lags the other or comes after the other. Like for example, for this case, the current lags the voltage by 90 degrees. It comes after the voltage by 90 degrees because of the difference, because of the derivative. This is one of the specification of the inductance or the inductors in general. Like the current lags the volt by 90 degrees, or the voltage leads the current by 90 degrees. Both statements are equivalent, both are correct. Makes sense? So this is one of the specifications that you should understand about the inductance, and the main reason behind this thing that the voltage is proportionally related to the derivative. The reason is why the voltage and the current, they do have different phases. They do have different phase angle. Why the current lags the voltage, why the voltage leads the current by 90 degrees. The main reason is that the voltage is proportionally related to the first derivative of the current over the inductor. Make sense? So if I ask you to try to write a relation between, or we can do like kind of changes here. How about if I decided to use the same phase for both of them? If I decided to apply the same phase for both of them. So if we decided to consider the same phase for both of them, we can do a little bit changes, or in other words, we can do it like this way. Like we can rewrite the volt, this volt, into this form in terms of Im, and we're gonna add here like negative 90 degrees, then we have to add here positive 90 degrees, because this multiplication, if you remember the operations as we discussed in the previous video over the phasors, like the multiplication of two phasors, you're just gonna add the two angles. So if you decided to add here negative 90 to have the same phase like the current, so you have to add here another angle of positive 90. Then if we consider this positive 90, this term together as a single term, and we're gonna consider Im with this angle, phase angle, as a single phasor. So this term Im with this angle is gonna give us IL, which is this phasor, and this omega L angle 90, this is gonna give us another phasor. So this is like the multiplication of two different phasors. This is one phasor, this is another phasor. Make sense? We can do it in this way, or another method. For example, how about if I decided if I ask you to find how much is Im from this phasor in terms of the phasor IL. So this definitely I can divide. Looks like you're already dividing both equations by the angle theta negative 90 degrees, and this by the angle theta negative 90 degree, right? So this angle will be cancelled with this angle. So you're just gonna end up with Im. It's gonna be IL divided by this angle. To remove this angle on the top, you have to switch the signs, right? So this is gonna give us like negative theta plus 90, as we explained over the previous video for the operations over the phasors. So simply from this equation, we can write Im. It will be like IL, but but remember that this is the phasor and this is the magnitude, and this is gonna be the angle theta is gonna be like negative theta plus 90 degrees. Then your objective is just to substitute for this thing and to replace the IM. So this is gonna give us VL will be, the new IM is gonna be IL times omega L times the angle which is negative theta plus 90 times another angle which is theta negative 90. Make sense? If I ask you to combine these two angles together, no, there is no negative 90 here, by the way. Yeah, we forgot this one. It shouldn't be here. There is no negative 90. So there is no negative 90 here. Make sense? It is just one angle, theta. This is originally, it should be theta from the previous term, right? So I added this negative 90, but I forgot to remove it. So we're going to end up with this case. If this is going to be like the multiplication of two phases of two different phasors, so we can combine, how we can combine these two into one phase angle, you have to sum the angles. So summing the angle negative 90 plus, negative theta plus 90 plus theta, this is going to give us positive 90. So simply this term will be just positive 90 degrees. So this is going to give us positive 90 degree. This is going to give us the volt in terms of this is the voltage phasor, this is VL as a phasor, and this is the current as a phasor. So this is the voltage phasor in terms of the current phasor times something. This something is just going to be a constant. We're going to deal with this term as a constant. So we're going to call it like ZL. Let us just, because this is just a constant value, this is an angle, and omega L is just a constant, but this is phasor, this is another phasor. So this is how the voltage phasor over the inductor is connected or is related to the current phasor over the same conductor, that it is looks like it is Ohm's law. Like this is like a resistance, right? Like this is in the Ohm's law, we do have the volt, it should equal to constant, which is the resistance, times a current, right? This is Ohm's law. This is the conventional Ohm's law in general. If this constant is resistance, this is going to be the Ohm's law for resistor, and this is what commonly known about the resistors, right? So it is very similar form of the conventional Ohm's law for the resistors, but this another equivalent form, but for an inductor. This form, we end up with this form when we converted the voltage form into phasor form and the current sinusoidal form into another phasor form. So over the inductor, the voltage and the current in the phasor forms, they're gonna have the same Ohm's law, and they're gonna be related or proportionally related through a constant. This constant is gonna commonly known as ZL, and this ZL is the impedance of the inductance that we're already talking about. So this ZL, this is the impedance for this inductor. So by representing this ZL, as you can see, ZL I'm presenting as J, which is the negative square root of negative 1 omega L. This is equivalent to the angle 90, because if we converted this one into cosine and sine, the cosine 90 is 0 and the sine 90 gives 1. So that's why you're going to have an imaginary. This is going to be imaginary. Makes sense? If you just converted this one into the cosine and sine form, as we did before, so the cosine 90 just 0, and the sine 90 gives 1, because it should be cosine. It should be cosine 90 degrees plus J sine 90 degrees. This should be multiplied times WL, which is omega L. So this term is 0, this term is 1, so this is gonna give us JL that I'm talking about here. So that's why we already have it here, JL. This ZL is known as the impedance of the inductance, or impedance for this inductor. This impedance, this is like an equivalent resistance for the inductor, but in the frequency domain. As you can see, this impedance depends on the frequency omega. It is not constant like it is not dependent over the time, and instead it is dependent over the frequency. So that's why we're already moving to another domain. There is no time dependence at all in this equation, in this term. We have only frequency dependence. So this is known as moving to another domain, which is the frequency domain. When we try to move the electrical circuit, or we convert the inductance into the frequency domain, we're gonna end up with impedance. And because of this impedance, the inductor can be treated as an equivalent resistance. We're gonna deal with it like any regular resistance, and we're gonna apply the fundamental law that we already covered in chapter 2. This is the basic idea of the impedance. The same thing can be applied for the capacitance. If we do have, let us assume that we do have a capacitor like this one, and this capacitor, there is voltage over the capacitor, like there is a specific voltage over this capacitor as Vc as a function of time, that as already given, Vm, this is the peak, the cosine omega t plus theta. So how much is the current over this capacitor as a function of time? We knew from chapter 3 that the current over the capacitor as a function of time, it can be related to the voltage using C, or proportional related to the derivative of the voltage, which is dVc by dt. So what is the derivative of this volt? Is going to give us the C, it will be constant. The derivative is going to give us the Vm times omega sine, and there should be like negative, C Vm omega, the sine of omega t plus theta, right? So this is just the derivative of this function, and the C just constant. This is gonna give us the current as a function, current IC as a function of t. Make sense? So if this is the current and this is the voltage, and we decided for some reason to convert them into phasors. So what is the Phasor form of the Vc of t? It won't gonna be as a function of t, it will be in the frequency domain. There is no function of t. This is the Phasor form. So the Phasor form is gonna be Vm, and the angle definitely is gonna be theta. Very simple. But how about this form? This is already in the sine, so it should be converted to the cosine. To convert to the cosine form, you should have here negative 90. So the current IC, it will not be a function of time. This is the Phasor form. Its magnitude value will be negative. If you want to get rid of this negative here, we can move this negative inside, because if you remember, like one of the specification of the sine function, that we can move this negative inside here, right? So adding this negative inside and doing the multiplication to these two terms, instead, and try to convert the sine into the cosine. So instead, the equivalent form, it will be C Vm omega, the cosine of omega t plus theta plus 90 degree, as already given here. This is the equivalent form. So we conventionally add negative 90 degree, right, to the cosine, to convert from sine to cosine. But this angle, this negative, to include it inside, this is gonna convert this angle, is gonna, instead of adding negative 90, is gonna be positive 90, to get rid of this negative in the front, and the magnitude of this of the current. So the current phasor in this case, this constant, this is gonna be the peak, it's gonna be the C Vm omega, and the cosine, the angle in this case is gonna be theta plus 90 degree. So as you can see that the current is already leads the voltage by 90 degree. It comes in front of the voltage by 90 degree. It is opposite to what we mentioned for the inductance. So for the capacitance, the current leads the voltage by 90 degree. This is a correct statement. Also, if we said that the voltage leads the current by 90 degree, also it is a correct statement. It is totally opposite to what we mentioned for the inductance up there. We can do the same. We can try to apply the same phase for both of them. So if we added, like we have to add plus 90. So if we added positive 90 here, plus 90 degrees, we have to subtract negative 90 degrees to have the same phase, right? So rewriting this phasor of the volt into this form, so the Vc, it can be written as, into this form, Vm, and the angle, or simply we can come up with the Vm from this expression, because we would like to find the relation between the volt as a function of the current itself. So anyway, the volt is gonna be like, the angle here is negative 90 degrees, and there is another common angle which is theta plus 90 degrees here. Make sense? So this is just the Vc form. Then what your objective is just, if we decided to multiply, just multiply this one times C omega divided by C omega. So you're gonna multiply times C omega, then you're gonna divide here times 1 over C omega. So we didn't change the value, right? So this term, as you can see, this angle with this magnitude, this should give us IC, right? According to this equation. These two terms together form the IC, which is C omega Vm. The angular is theta plus 90, right? So this definitely gonna give us, we can end up then, the VC can be written as 1 over C omega, which is this term, the angle or times IC with angle negative 90 degrees. Make sense? This negative 90 degree, it's gonna give us 1 over J, and the J is gonna be in the denominator. It means that this term we can write VC as 1 over J, which is square root of negative 1 C omega times IC. So this is also a very similar form to the conventional Ohm's law, and this is gonna be the constant. There is a constant value. This constant, we're gonna call this one as ZC, and this is gonna be the impedance. This is gonna be the impedance for the capacitor of the capacitance. So the impedance of the capacitance, we proved that it will be 1 over J omega C, and this impedance, if we consider it, we already like kind of converting the conventional capacitor into an equivalent resistor. Make sense? So this is the basic idea of the impedance, and this impedance is they already show up as long as or at the instant that we try to convert the inductor or the capacitor from the time domain to the frequency domain using the Phasor form. So this derivation here, I was just trying to drive to you that the impedance of inductance, it is J omega L. The impedance of the capacitance, it is 1 over J omega C. It is all the time for any capacitor, for any inductor, JC is fixed expression. It's gonna be 1 over J omega C for the capacitance and J omega L for the inductors. Make sense? This is for the impedance. So generally speaking, we can define impedance, it means complex resistance. So as you can see, it is a resistor. It looks like a resistor, but in the complex domain, or over the complex plane. That's why it is like complex number, and that's why we already explained in the start of the chapter. We did like a review over the complex number, and this is gonna be like another equivalent resistance, but in the complex plane or in the frequency domain. The impedance concept is equivalent to stating that the capacitors and the inductors act like frequency-based resistors. So they are resistors, yes, but their performance depends on the frequency of the voltage or the current through the electrical circuit. So what does it mean? It means that, as you can see, ZC, it will not be constant value. It will be dependent on the frequency of the voltage source and the frequency of the current roaming within the electrical circuit. So if we increase these frequencies, the ZC and ZL will be increasing. But if we are decreasing the omega, which is the frequency of the volt and the current through the electrical circuit, these impedances will be decreasing as well. So they depend on the frequency. So that's why we can call them as frequency dependent resistors. These are equivalent resistors, but in the complex domain or the frequency domain. Make sense? The impedances can also be used to solve, and this is what we're gonna use. This is the approach we're gonna use. The good thing of this impedance that provide us a very simple form of the electrical circuit. Once we convert the electrical circuit from the time domain to the phasor domain, from the time domain to the frequency domain, or using the phasors, we're gonna automatically end up with these impedances. These impedances, we're gonna treat them like the already conventional resistors within the electrical circuit, so we can easily do analysis for the electrical circuit. But remember that this is only allowed as long as we are interested in the sinusoidal analysis or sinusoidal analysis of electrical circuit. And the other condition, there is two conditions here, should be steady state, and the voltage and the current should be in the sinusoidal form. So we could able to use this impedance to do analysis for electrical circuit. So in general, we discussed through this course that the electrical circuit would include a source of voltage, there should be a current and other electrical element like capacitors, inductors, and resistors. So what is the key idea of this method to convert from the time domain to the frequency domain? Your objective is just to convert the original electrical elements into impedances, into equivalent resistors in the complex domain. These are the impedance. So the resistor, the resistance, its equivalent impedance is just R. So the resistance itself, it is already impedance. There is no need to do any conversion. It is automatically like impedance. So the impedance of a resistance, it is the resistance itself, equal the resistance. But the impedance of inductance, it equals J times omega L. The impedance of the capacitance, it is 1 over J omega L. For any capacitance, for any inductance, for any resistors, this table is applicable. We can apply with this all the time. This is the expression for the impedance for resistor, capacitor, and inductor, whatever it is. Make sense? So this is the key idea of the impedance, the procedure, how we can use this impedance thing and the phasors. Phasor and impedance mean that we're gonna convert to the frequency domain. So the general procedure to use these things for these for electrical circuit analysis, for the steady-state electrical circuit analysis, the first step, your objective is just to represent the circuit in the frequency domain. Convert the circuit from the time domain to the frequency domain. How? Simply, if you don't have volt, rewrite the volt in the phasor form. The volt will be given in the frequency form. Your objective is just to convert this voltage into the phasor form, as we explained. Choose the get the peak value and the phase angle, so you're already converting it into the phasor form as we did before. The same thing for the current. If there is any given current to you in the electrical problem, your objective is just to convert this current into phasor. So for any given current or voltage, convert it into phasors. This is one thing. Also, convert any resistor, capacitor, inductor into impedance. If we did so, we already converting or driving an equivalent form of the original electrical circuit from the time domain to the frequency domain. This is how we can convert the electrical circuit from the time domain to the frequency domain. Simply convert any volt and current into phasors, converted any resistance, capacitor, and inductor into impedances. Impedance according to this table, phasors as we explained before. Then what? So replace the sinusoidal, how we can do over these two statements. As I said, replace the sinusoidal form of the voltage and the current sources by their equivalent phasor form. Replace the inductance, capacitance, and resistance by their equivalent impedance according to this table that we already explained. Make sense? Then once we convert, your objective, now you are dealing, once we convert to the frequency domain, this new electrical circuit is going to be typically the same like the resistive electrical circuit that we explained in chapter 2. And your objective is just to choose any one of the four methods that we explained in chapter 2 to do analysis to this resistive circuit. It is equivalent resistive circuit. Make sense? So analyze or do analysis to the circuit using any of the four methods of resistive circuit analysis that had been explained in the chapter 2. Once we do the analysis and we find analysis, what does it mean electrical circuit analysis? As we said many times, it means that to come up with the unknowns. Once you find the unknowns, your objective is just to convert back, do the calculation and convert back. You're gonna do some complex algebraic calculation as I'm gonna show you over, like you're gonna work over the phasors as I'm gonna show you in the next example. Then once you find the unknown, your objective is just to convert back from the frequency domain to the phasor to the time domain back again. Okay, so then let us consider this next example as more demonstration over this procedure, but this is the general procedure and how it works for the phasors and impedance and how we can use the conversion from the time domain to the frequency domain to do analysis for steady-state analysis for these electrical circuits. So for this electrical circuit, it is required to find the steady-state current. So this is one requirement, the steady-state current, which is I of t. But this in the steady state, which is this current as a function of time, but in the steady state period, we don't care about the transient period of the current because we said that it dies out very quick. So it is very negligible, and we just interested in the steady state, so we can apply the impedance method and convert to the frequency domain. Also, it is required to find the phasor voltage across each element. We do have three elements: resistor, inductor, capacitor. How much is the volt over this one? But it is not just any regular volt. We need the phasor voltage over these three electrical elements. Then we're gonna construct a phasor diagram, which is like this one. We're just gonna represent the relation between these three phasors as already given here. Like, we're gonna draw a diagram similar to this one for the voltage over R, the resistor, the capacitor, and the inductor of this electrical circuit. So let us stick to the procedure. What was this first step? Convert to the frequency domain. How? Convert any current, given current or voltage, into phasors, and convert the electrical element into impedances based on this table, right? So remember that R, it should be R, its equivalent impedance, the impedance of L, J omega L, and for the capacitor is 1 over J omega C. Make sense? So one of the first things that you have to do, you have to figure out how much is omega, the frequency within this electrical circuit, assuming that the current and the voltage both, they already using the same frequency or having the same frequency. According to the given voltage here in the sinusoidal form, the frequency is already 500, so it should be 500 radian per second. This is the frequency. And T, this is the time, the phase of this voltage source is 30, and its magnitude is 100. And this is R, the resistance of the capacitor, the resistor. This is the inductance of the inductor, 0.3 henries, and the capacitance is 40 microfarad, right? So your objective is just to convert these things into their equivalent impedance and phasors. So how about the equivalent phasor to this volt? It should be like 100, and the angle definitely is going to be 30 degrees as long as this cosine. So you're going to get rid of the cosine and omega t, and you're just going to use the phase angle and the peak or the amplitude. So this is the phasor form of this voltage. There is no specific expression given to us. We have to solve for the current, so there is no need to express any phasors for the current so far because we don't have this form yet. But we have to convert this R into impedance, this resistance into impedance. What is the impedance of this R? It should be the same value. So the impedance ZR, it should equal to this one, it should equal to 100. And forget about the unit for now. Make sense? How about the impedance for this L? The impedance for the L, ZL, it should equal to how much? It should equal to the 0.3, which, or the expression, it should be J omega L, right? How much is omega? It is 100, and L is 0.3. So if we did the calculation, 500 times 0.3, this is going to give us 50 J. So this definitely, its ZL is going to be J50, and it is complex. How about the C? The C, it's ZC. According to the table, it should equal to 1 over JC omega. So this is going to give us C, it should be 40 times 10 to the power negative 6. So it should be 1 over J. The C, it should equal to the 40 times 10 to the power negative 6 times the omega, which is 500. If we did the calculation, and we can, by the way, move this J onto the top by negative J. We can move it to the top as negative J. So this at the end gonna give us negative J. It means that 1 over J, it is equivalent to negative J. And 1 over 40 times 10 to the power negative 6 times 500, this term will give us 50 as well. If we did this calculation, we're going to end up with 50. So this is ZC and ZL as already given here for this electrical circuit. So simply, we end up with another electrical circuit, and this is the first step in the frequency domain. Like we do have here resistor. This resistor now it is ZR equals 100. And we do have here inductor, and with ZL equals J50, and we do have a capacitor with ZC equals negative J50, and we do have a voltage source here, plus and minus. This voltage source is given Vs by 100 and the angle 30 in the phasor form. And definitely there should be a current roaming within this electrical circuit. It should be IS, but it won't gonna be function of time. No, don't type it as function of time. We move to the frequency domain. There is no function of time anymore. Make sense? Then your objective is just to solve this new electrical circuit. This electrical circuit, you can apply Kirchhoff voltage law to end up with the current. You are required to find the steady state current. Solve for the current for this electrical circuit. So simply if we applied Kirchhoff voltage law to this electrical circuit, we're gonna end up this voltage source, it should be negative Vs because this is the input, plus the voltage over the resistor, plus the voltage over the inductor, plus the voltage over the capacitor. All of these are outputs. It should equal to 0. How much is Vs? Vs is already given to us by the negative. We got it by negative angle 30 degrees. This is the Phasor form. Plus, how much is Vc? Vr. Vr, it should equal to the Zr times Is according to Ohm's law. Apply Ohm's law. This is like resistance. So it should be the resistance Z. Now the resistance, it is just named Z times the current over this resistor, which is Is. So it's gonna be Zr times Is plus how much is the current over this, or the voltage over this VL? VL, it should be ZL times Is, the current times the resistance. So it's gonna be ZL times Is plus VC is gonna be also ZC times Is equals 0. And there is no need to substitute for these now. Just keep the impedances with their Z form. Don't plug their values till the end. Even it is advised to keep this Vs as it is for now, but that is fine even if you substitute. This term is just negative. This term is negative Vs. So is it fine if we took this Is as a common factor? Yes. So we're gonna end up with negative Vs plus Zr plus ZL plus ZC. All of these impedances can be summed together time Is equals 0. So if I ask you to solve this equation for the Is, let us call this term as Z equivalent. This is like equivalent resistance, because according to chapter 2, if these are 3 resistors, they already in series, right? And the equivalent of these 3 resistors, it should be Z equivalent, their sum. So if we give this one a name as Z equivalent, so what should be Is according to this equation? So Is according to this equation is gonna be the Vs divided by Z equivalent. How much is Vs? We already got it in the Phasor form as 100, the angle is 30 degrees, over Z equivalent. Your objective is just to find Z equivalent, where Z equivalent, it should equal to the Zr plus the ZL plus the ZC. Now here you can plug their values. How much is Zr? We got it by 100. Right, it is 100 real value, but ZL it is J50. It is a complex value or imaginary value, and the GC it is also a complex value. So it should be plus 50 J. This is the ZL, and negative J50. This is gonna be the ZC. Make sense? So there is like some correction here, like this ZL, it should be J150, 150, not 50. Just a mistake here. There should be 150 as value, and definitely this is gonna be like 150 here. So let us do this correction. But anyway, it's gonna be nothing is gonna be different than what we explained. That just I did the wrong calculation. The 0.3 times 500 should give us 150. It is not 50. So I did like a little bit mistake in the calculation. So anyway, so this ZL, it should be 150. This term, it should be 150 here. So having this term as 150, negative J50, this is gonna give us 100, which is a real number, and 150, we have to do the calculation, we have to do the summation to the complex number or the imaginary term and the real term. This is real term, it just, and there is no any other real term, so it's gonna be 100, and just sum the imaginary terms. 150 negative 50 gives positive J100. So this is gonna give us the Z equivalent. Then plug this Z equivalent here and do the calculation for the Is. But to do the calculation for the division, we said that if you remember from the Phasor form, for the operation, it is advised to do the division or the multiplication of the phasors in the Phasor form. So what does it mean? It means that your objective is just to convert this complex number into the Phasor form. How we can convert this complex number into the Phasor form? The equivalent, Z equivalent into the Phasor form, which is 100 plus J 100, its equivalent Phasor form is going to be the square root, which is the magnitude of the 100 square plus the 100 square. The magnitude of the real square, the square root of the real square plus the imaginary square under the square. This is going to give us the magnitude. And the angle, it should be the tan inverse of what? Of the magnitude of the imaginary divided over the real, but they already equal. So the tan inverse of 1 gives 45 degrees, and this is going to give us 100 square root of 2. So this is going to give us 100 square root of 2, and the angle is going to be 45 degrees. So this is the Phasor form of this Z equivalent. Now we're gonna plug this one here into this equation. Let us give this equation as equation 1. So now we're gonna substitute into equation 1. So we're gonna end up with IS into this form. The VS, it is 100, and the angle, it is 30 degrees, and this form, it is 100 square root of 2. The angle, it is 45 degrees. So how we can do this division? Your objective is just to divide the magnitude over the magnitude, which is 100 over 100 square root of 2. Then you're going to subtract the angle, 30 degrees, negative 45 degrees. Doing the calculation, this is going to give us 1 over square root of 2, which is going to give us 0.707, this calculation, this term, and the angle definitely is going to be the negative 15. So this is going to give us the IS. We're going to end up with the IS into this form. This is the IS in the Phasor form, will be the 0.707, which is 1 over square root of 2. The angle is negative 15 degrees. This is the current in the Phasor form. Then can we convert it into the time form? Yes, we can. Remember that it is required from us to find the steady state current. So the steady state current, it should be in the time domain. Now we got the current in the frequency domain as a phasor. We have to convert it back into the time domain. How we can convert it to the time domain? How we can switch the Phasor form into a sinusoidal form? This should be the peak, the magnitude, which is 0.707, and you're gonna add here the cosine, and you're gonna add the omega t negative 15, which is the angle. Omega, it should be the 500. So this is gonna give us the steady state current. This is gonna be the steady state current for this electrical circuit, right? But remember, to be more accurate, we have to use a different like this is the IS. So equivalently, the current in the time domain, this is the steady state current. The steady state current in the time domain is gonna be the 0.707. This is the magnitude, the cosine of 500t, which is omega t, negative 15 degrees. This is gonna give us the steady state current. If we decided to plot this function, we're gonna end up with a wave that represents the current within the steady state region of this electrical circuit. And this is the first part. It's just to find the steady state current. Then it is required to find the phasors. Voltage across each element. We have 3 elements. How much is the voltage over this element? How much is the voltage over the second element? This is what we would like to end up with, right? So your objective is just to write the voltage VR over the resistor. It should equal to R times it should equal to ZR times IS. This is in the Phasor form. How much is ZR? We got it by 100, right? ZR, it is 100 times the Phasor form of the current, which is 0.707, and the angle is negative 15 degrees. So doing the calculation, your objective is just do this calculation. So it's going to be 70.7, and the angle is negative 15. This is the phasor of the voltage over the resistor. He didn't require any time domain. He didn't require this voltage in the time domain. He didn't mention voltage. Find the voltage over the electrical element. If he required the voltage over each electrical element, we have to convert this phasor form into a sinusoidal form, into the time domain. Now we are working in, for this V, we're already working in the frequency domain. If he required the voltage over each element, we have to convert it to the time domain. But if he required, as he mentioned here, he required the phasor voltages. So this is the phasor voltages, and he didn't require any voltage. So if he just mentioned voltage, this indicates the voltage and the time domain. It should be in the time domain. But phasor voltage should be in the frequency domain in the phasor form, as already we got it here. So we won't gonna do any further things to this step. Now we're gonna calculate the voltage over the inductor. The voltage over the inductor should be ZL times IS. ZL, we got it by ZJ150. Make sense? Times 0.707, the angle, it should be negative 15 degrees. This term, this J, we can convert it into the polar form as 150. This is the magnitude, and the angle directly is going to be 90 degrees. Because this is like in the rectangular form, we have to convert it into the polar form. So this term, there is no real, it means that the angle, it should be 90 degrees. If you expanded this one into cosine 90 plus J sine 90 degrees, this is going to give us 1, this is going to give us 0, right? So this is going to give us J times 150. It should be here. So this term is equivalent to this term, and this is its polar form. We need it in the polar form so we can do the multiplication for these phasors, and this is what we're going to do. So simply, if we did the multiplication, we're going to multiply 150 times this constant value. So this is going to give us the 150 times 0.707. This is going to give us 106.1. 06.1. And the angle, your objective is just to sum the two angles. 90 plus negative 15 gives 75 degrees. Make sense? So this is going to be the VL in the phasor form. How about the VC over the capacitor? It's going to be ZC times IS equals the negative of J50. This negative term, it can be converted. It is equivalent to 50, but the angle negative 90 degrees. Very simple. So if it is positive J, it's going to be 90. If it is negative J, it's going to be negative 90. Very simple. Make sense? Times the 0.707, the angular is negative 15. Then you're going to do the multiplication of the constants, the 50 times the 0.707. This is going to give us 35.4. Then you're just going to sum the angle. Negative 90, negative 15, this gives negative 105 degrees. Then if we decided to plot these three phasors, all of them together, starting, so this is the phasor, the second phasor, and this is the third one. So your objective is just to set up like x-axis and y-axis, like two axes. In this way. And you're going to consider this horizontal x-axis, which should be the real axis, and this is going to be the imaginary axis. So you're going to consider this is your main reference. If the angle is positive, you have to rotate clockwise counterclockwise direction. If it is negative, you have to rotate clockwise direction. So for the VR, we're going to rotate negative 15. So your objective is just to try. Assume that you just measured angle of negative 15 in the clockwise direction. Then you're going to draw a line. This is going to give us V1 vector, the first vector, with angle negative 15. How about the second angle? It should be 75. It is positive, so we're gonna rotate in the clockwise direction. In this direction, we're gonna rotate 75 degrees, and we're gonna draw another angle, which it should be this one, like V2. Try to make the relation between V1 and V2 in terms of the length of the arrow itself. It should be like kind of consistent with the values. Like as you can see, the VL, it should be bigger, longer, and the VR, it should be shorter. So it means that V2, it should be a little bit longer here. And this is what we're gonna do. Like in this line, when I try to draw the VL, this is gonna be VR. The VL, it's gonna be longer because it has a bigger value. So this is gonna be VL value, and this is the angle. How about the VC? It should be shorter than both, and its angle is negative 150. Negative 150, it means that you're just gonna rotate all the way 90 degree, and you're gonna move further in the other third quadrant. So it's gonna be located somewhere here. This is gonna be the V, and remember that it should be shorter. So this is gonna give us the VC, and this angle, it should be the negative 105 degrees. So this is the phasor diagram that represent how these phasors are already related together. So for example, if I ask you to describe the relation between VL and VR, so we're gonna say that VL, it leads VR by 90 degrees. Why? Because the angle between VR and VL is 90. And VL, it comes before first. So the first thing, it means that we're gonna say that we can write this statement: VL leads VR by 90 degrees. This statement is correct. Also, we can say that VL leads VC by how much? How much is this whole entire angle? It's gonna be the 75 plus 105, which is gonna give us 180 degrees. It means that it should be leading VC by 180 degrees. It means that these two lines should be considered as single line if we're already drawing to scale or accurate, right? So it should be leading by 180 degrees. How about the VR in relation to the VC? So VR leads VC by how much? How much is this angle? If you subtract 150 negative 15, this is gonna give us the difference. So this is gonna give us negative, it's gonna give us, like, forget about the signs, it's gonna give us 90 degrees. So it leads by 90 degrees. But how about the VR? It lags the VL by 90 degrees, and so on. So this is, all of these statements are correct. So this diagram represents the relation between these different phasors in the frequency domain. Make sense? And this is what was required from us through this example. Simply, it's just to find the steady state current. It should be in the time domain. The phasor voltage, it should be in the frequency domain. But if he required the voltage over each element, and he didn't mention phasor, this voltage should be in the time domain. And also it was required to construct the phasor diagram, and this is the thing that we already did for this electrical circuit. Make sense? So let us consider this example 2, and this is going to be the last example for this video. It is required for this given electrical circuit to find the voltage across the capacitor, VC. And he mentioned voltage. It means that we need VC in the time domain. He didn't mention phasor voltage. Make sense? But he required the phasor current through each element. We have so many elements. The objective is just to find the phasor current over the capacitor, the resistor, and the inductor, and construct a phasor diagram. Definitely is going to be for the current. So how we can solve this electrical circuit? We're going to stick to the procedure. Your objective is just to come up with the omega value, how much it is. Omega from this function, this is already in the sine form, so it should be first converted into the cosine form. So it's going to be the 10 cosine omega, which is 1000 t negative 90 degrees. This is the cosine form, right? So as you can see, omega is going to be 1000 radian per second. This is going to be omega for this voltage source. And this is going to be, then you're going to convert this one into phasor. So if we draw the electrical circuit one more time, this is going to be coil. You can even just put here like a box, because anyway this is like impedance, which is like all of them is going to be different impedances. But anyway, and we do have here like resistor, or you can just add a box without drawing the resistor itself, and you're going to have here another box for the capacitor. In this way, to keep in mind that all of these are different resistors. And we do have here the voltage source, plus and minus. So this is the Vs, right? So this is in the frequency domain, this is in the frequency domain, and this is in the time domain. And the frequency domain, Vs is going to be 10, the angle is going to be negative 90 degrees. Very simple. This is the phasor form of Vs. How about this one? It should be ZL. How much is ZL? The equation should be J omega L. Omega is 1000 times L, which is 0.1. This is going to give us 100, right? So this is going to give us J 100. L is 0.1, 1 times 1000, which is omega. This is going to give us 100, and J. The R, it should be 100, so ZR here is going to be 100 ohms. And for the ZC, it's going to be, the expression, it should be 1 over J C omega. So the C here is already given by 10 microfarad times omega, and this one is just 10 times to the 10 to the power negative 6 times omega, which is 1000, which is 10 to the power 3. If we did the multiplication of this term and we moved like 1 over C omega, this is gonna give us like, and we even move the J to the top, so it's gonna be like negative J, and the omega, the C times omega, this is gonna give us 100 as well. Make sense? So we converted from the time domain, the electrical from time domain to these to the frequency domain. Now your objective is just to deal with this electrical circuit and find, it is required to find. This depends on the requirement. We have 4 methods of solving the resistive circuit. You're gonna deal with this electrical circuit like it is resistive electrical circuit. All these elements are resistors. So you can apply any one of the 4 methods that we explained in chapter 2. But this mainly depends on the requirement. It is required to find the phasor current through each element, or in other words, the current. We are interested in the current over each element. So for this one, it is recommended to apply the Kirchhoff current law, voltage law for this, and Ohm's law for this electrical circuit. So we're gonna start here by applying, apply the Kirchhoff voltage law, current law, Kirchhoff current law, and Ohm's law to this electrical circuit. So for example, if we apply the Kirchhoff current law, first step, if you remember that we have to distribute the current. So the current here, it should be IS, this is the total current, and the current over this element will be definitely IS. Still at this node, it will be split into 2 currents, I1, and we're gonna have here another current over IZ as I2. So your objective is just to find how much is IS, how much is I1 and I2, and this is gonna be node number 1. So what you're gonna do, you're just gonna apply Kirchhoff current law. Apply Kirchhoff current law at node 1. Kirchhoff current law at node 1, it should give us the IS, it is input, and the output equals I1 plus I2. Remember that all of these IS and I1 and I2, these are phasor, and this is gonna give us the first equation. Remember that the unknowns are 3 currents, these main 3 currents. Then we're gonna apply the Kirchhoff voltage law. Since we have 3 unknowns, so we should have 3 equations, right? One equation is gonna be the node voltage, and we're gonna apply for loop 1 and Kirchhoff voltage law for loop 1 and loop 2. So for loop 1, how many voltage do I have within this loop? We do have 3 voltage. The Vs, it is input, so it's gonna be negative Vs. And we do have the voltage over the inductor, which is plus VL, it is output, and the voltage over the resistor is gonna be plus VR, it is also output. Make sense? This should be 0. How much is VL and VR? Just keep VL in the symbol form. So this is gonna give us VS in the symbol form as it is, and don't substitute with things except the VL and VR. How much is VL and VR for this electrical circuit? VL, it should equal to the IS. What is the current over this resistor? It is IS times the resistance, which is J100, J100, but don't substitute with the values, just substitute with ZL, work in the simple form. So this is gonna give us like the plus of IS times ZL. This is the VL, plus the voltage over VR. How much is the current over VR? It is I1. The current over VR, it is I1. So it's gonna be I1 times ZR. So it's gonna be I1 times ZR, like it is resistance, equals 0. And this is gonna give us the second equation. How about the third equation? You're just gonna apply the Kirchhoff voltage law to loop number 2. For loop 2, we do have 2 voltages, ZC and ZR. So one is input, the second one is output. Even if you rotate with the current, with the assumed direction of the loop, this direction is opposite to the I1 and the same direction as I2. So ZR is going to be negative, or the voltage over ZR is going to be negative, and the voltage over ZC is going to be positive. So this is going to give us the loops. The second loop is going to be negative VR but positive VC equals 0. How much is VR? We got it by the negative I1. How much is the current over this resistor? It is I1 times ZR. How much is the current over this one? It is I2. This is resistor times ZC. So it's going to be the negative I1 times ZR plus the I2 times ZC equals 0. So we can write this equation into this form like I2 ZC equals I1 times ZR, and this is going to give us the third equation. Now we got three equations in three unknowns, I1, I2, and IS. Solve them and work in the simple form first, initially. So, for example, to solve the equation, and this is going to be so this is the second step, is just to drive this equation. The third equation, just solve for unknowns. Again, what are the main unknowns that we are seeking within this electrical circuit are the currents, I1, I2, and IS. So how we can solve for these unknowns? Simply, from equation, we can start from equation 3, or any equation. From equation 3, we're going to conclude that I1 equals ZC divided by ZR times I2. Make sense? And let us give this equation like equation A. Then what? You're just gonna plug this equation into any one of the other two equations, equation 2 or equation 1. So for example, substituting into equation 1, we're gonna end up that IS, which is equal I1 plus I2. So I1, we got it by the ZC over ZR times I2 plus the I1, the I2, right? So from this equation, we can find the I2 in terms of IS. So it's going to give us the IS equals I2 times 1 plus ZC divided by ZR. Okay? Then plug, so this give it like equation B. Then substitute into equation 2, the second equation. So into the second equation, we do have here the negative VC, IS that we already got it here. So this is going to give us the negative VS, the IS, which we got it by I2 times 1 plus ZC divided by ZR. This should be multiplied. This is just IS. This is just IS. And as you can see here, the IS is multiplied times ZL plus I1 that we already got it times ZR. So this is going to give us like the plus times ZL plus the I1, which we already got it in terms of I2, and we do have the I2 in terms of IS, right? So this is going to be like, we can write this one as ZC over ZR times I2. Then we're going to plug, substitute for I2. I2 from this equation B, I2 from equation B, it had this expression. So let us do it in another step. So this times ZR equals 0. Then we're going to get rid, we have to consider, or yeah, everything is already in I2, so there is no need. You have to make sure that you have only one unknown in one equation, which we already got it here. We already have I2, and this term is I2 as well. So there is no need to substitute for equation B. So from this equation, just collect the I2 as a common factor and do some simplification to this equation. We're going to end up with I2 with this expression. It's going to be VS divided in the denominator. You're going to find ZL plus ZR. This times the ZC divided by ZR and plus ZL. So this is going to give us the I2. Simply, if we already have everything except I2. We have VS, we have ZR, CL, and ZL. So we can plug these values in addition to the VS to end up with the I2. But to substitute with these values, we have to do some arithmetic work over the complex number. So that's why we explain these things, how we can do calculation or summation and subtraction, multiplication of phasors and complex number before, right? And this is what we're going to do. Your objective is just to plug these values for these ZC, ZL, and ZR. But let us do these calculations step by step. As you can see, we do have different forms of the calculation. We do have the summation of two complex number. And if you remember, from the complex number part, that the summation or the addition or subtraction of complex number should be done in the rectangular form, in the cosine and the sine form. But the multiplication or division, it is better to be done over the polar form. So we have to convert all the time from polar to rectangular, rectangular to polar, and so on to perform this calculation. So let us break it down. It means that let us first just consider ZL plus ZR. Just calculate this term, ZL plus ZR. How much is ZL? ZL, it is J100 plus ZR, which is already 100. So it is automatically done. It is 100 J100. This is a complex number. This is the first calculation. Very simple, straightforward calculation. No problem. Now let us calculate ZC over ZR. ZC over ZR. ZC, we already got it by the negative J100 and ZR is just 100. So to do division, this is in the rectangular form. This one, negative J100, indicate that this complex number is shown, is given or represented in the rectangular form. We have to convert to the polar form. The equivalent polar form to this one, as we mentioned once before, it is 100. The angle is negative 90. You can try it. You can type, expand it into cosine. Cosine angle plus I sine angle, the plus sine angle, it means you're gonna deal with this form, or you're gonna consider like, no, convert from rectangular to polar, you're gonna have like the real part square plus the imaginary part square under the square root. This is gonna give us 100, and the tan inverse of the imaginary, which is negative 100 over 0, gives the infinity. The tan inverse of negative infinity is negative 90 degrees. And this should be divided by 100. So automatically you have to consider this, memorize these things. Like if it is negative J, automatically it is equivalent to negative 90. If it is positive J, it is equivalent to 90, and so on. In case, as long as it is just imaginary term, there is no real term. So simply, if we did the calculation, 100 divided by 100, this is gonna give us 1. This is the magnitude, and the angle is gonna be the negative 90 degrees. This is ZC over ZR. Make sense? Then your objective is just to do the multiplication of these two terms together, right? So if we did the multiplication of the ZR, now let us do the multiplication of ZL plus ZR times the ZC divided by ZR. We got this one in the complex form as 100 plus J100. This is in the rectangular form, times the 1 times the angle, which is negative 90 degrees. To do the multiplication of two complex number of phasors, it should be done in the polar form, right? It is recommended to do it in the polar form. So it means that we have to convert this one into its equivalent polar form, which it should be the 100 square plus the 100 square under the square root. This is the magnitude. The angle, it should be the tan inverse. The angle, it should be the tan inverse of what? Of the 100 divided by the 100. So this equivalent form is gonna be, this is gonna give us 100 square root of 2, which is this term. The angle is gonna be 45 degrees. The tan inverse of 1 is just 45 degrees, times 1, and the angle is negative 90 degrees. So you're just gonna do the multiplication of the amplitude, which is gonna give us 100 square root of 2, and you're gonna sum the angles. 45 negative 90, this is gonna give us negative 45 degrees. This is gonna give us this summation. Make sense? Then what? Your objective is just to add this term to the ZL. We're still working with the denominator. So how much is ZL plus ZR times ZC divided by ZR plus ZL equals, we got this term by 100 square root of 2, angle negative 45 degrees. You're gonna add to this term ZL. ZL, it is, we got it by J100. This is ZL from the top, right? So this is in the rectangular form, this is in the polar form. To do summation or addition, we have to convert this one into polar, into rectangular form. So the rectangular form of this term, it should be the 100 square root of 2 times the cosine of the angle, which is negative 45 degrees, plus the J of the sine of the negative 45 degree. Remember that the cosine gets rid of the sine, but the sine reject the sign, the negative outside, right? So doing these calculations, we're gonna end up with a real number plus an imaginary number plus another imaginary number. So we're gonna end up with this term. The 100 square root of 2 times the cosine 45 degrees, this is gonna give us the 141.4, or let us do the calculation right away. So if we did the calculation of the 100 square root 2 times the cosine 45 degrees, this definitely is gonna give us 100. And the 100 square root of 2 negative, because this negative will be rejected outside, so it's gonna give us negative 100 square root of 2 times sine 45. This also gonna give us negative j 100, because this multiplication is gonna give us, so this term is this multiplication plus there is j 100 here. So this term will be cancelled with this term. It means that we're just gonna end up with a real value for the denominator. So this is the last value for the denominator. It is 100. So we're gonna end up that the current I2, it should equal to Vs. Vs, now we're gonna substitute for the Vs. Vs over 100. How much is the Vs in the phasor form? Vs, as we expressed it in the start of this problem, Vs, it is a 10 angle negative 90. So it should be 10 angle negative 90 in the phasor form. So it is 10, the angle it is negative 90 divided by 100. Make sense? So if we did the calculation, 10 divided by 100, this is going to give us 0.1, and the angle simply is going to be negative 90 degrees. This is going to give us the current in the phasor form. This is I2 as phasor. So now we just got I2. How about I1 and IS? We still have two other currents to calculate. So I1, according to this expression, according to equation A, I1 it is related to I2 through ZC over ZR, and ZC over ZR we calculated here by 1 angle negative 90. We did this calculation. If we didn't, we're gonna do it, okay? But we are lucky we already have this calculation already, so it should be according, this is from equation A. We're gonna end up that I1 it should equal to the 1 angle negative 90. This term, again, this is the ZC over ZR, times, it should be multiplied times the I2, which we already got it by 0.1, the angle it is negative 90. Make sense? So doing the calculation, this is going to give us 0.1, and you're just going to sum the two angles. Negative 90 gives angle of negative 180 degrees. Make sense? So this is going to give us the current as I1 in the phasor form. And there is no need to convert to the time domain. How about IS? IS, we're going to find it. This definitely is going to be from equation B. From equation B, we have the IS, it is I2 that we just got it, times the 1 plus ZC over ZR, and again, ZC over ZR, it is 1 angle negative 90. So this is going to give us the I2, which we got it here by 0.1 angle of negative 90 degrees times 1 plus 1 angle negative 90 degrees. This is the ZC over ZR. But again, to add to the 1, we have to convert this term into the rectangular form. It should be converted into the rectangular form. So this is going to give us 1 times the cosine of the negative 90 degrees plus j sine negative 90 degree, or it can be converted directly into negative j. Why? Because we said angle negative 90 is equivalent to negative j directly in the rectangular form. So you can either do the calculation or you can convert it directly into negative j. So this is going to give us, this will give us this term 0.1 angle of negative 90 degrees, and what is inside the parentheses is going to be 1 as a real value, negative j, 1 as imaginary value. Then this term, which is in the rectangular form, you're going to convert it into the polar form to do the multiplication times this complex number, right? So this is gonna give us the 0.1 angle of negative 90 degrees. This term in the polar form, it will be converted into 1 square plus 1 square under square root. This is gonna give us square root of 2, right? So this is gonna be like square root of 2, and the angle is gonna be the tan inverse of what? Of the negative 1 over 1, because the imaginary is negative 1 and the real is 1. So the tan inverse of negative 1 gives negative 45 degree. Of negative 1 gives negative 45 degree. So this definitely is gonna give us the multiplication time. So this is the first term times another term, which is gonna be square root of 2. The angle is negative 45 degrees. Doing the calculation, doing the multiplication, we're gonna end up with IS. So this is gonna give us at the end, this is gonna give us the IS equals 0.1 times square root of 2, which gonna give us the how much? 0.1414, and the angle is gonna be the negative 90, negative 45 is gonna be the negative 335 degrees. Make sense? So this is gonna give us the current IS, and in the Phasor form, as well as the current I1 and I2 in the Phasor form. And these are some of 3 of the requirements. It is required to find the phasor current through each element. Then we can represent the Phasor diagram as we did for the voltage in this diagram here. We can represent this thing. But in addition, it is required to find the voltage across the capacitor. So how much of the voltage over the capacitor? And the voltage, it should be in the time domain. So the voltage over the capacitor, it should be I2, according to this circuit, should be I2 times ZC, right? And we already got I2. So your objective is just to multiply times ZC to end up with the voltage over the capacitor. And this is the last thing that we're gonna do. So the voltage VC, which is the voltage over the capacitor. This is what we would like to calculate here, right? So we already have VC in the Phasor form. This is Phasor in the Phasor form. VC, it should equal to how much? It should equal to the I2 times ZC, as we just mentioned. I2, we already got it in this form. I2, we got it by the 0. This is I2. 0.1 angle negative 90. So it's gonna be 0.1 angle of negative 90, and ZC, it is already given by the negative J100. This negative J, we can convert it into angle negative 90 directly, right? So doing so, we're gonna end up, we can convert this one into 100 angle of negative 90 degrees. So doing the multiplication, this is gonna give us like 10, right? This is gonna give us 10, and we're gonna have here the because this is 100 times 0.1, and the angle is gonna be the negative of 180 degrees. So this is gonna give us the VC, the phasor, but in the voltage over C, but in the Phasor form. This is in the Phasor form. We have to convert it. This is the Phasor voltage. We need it as a voltage. He didn't mention Phasor voltage. He just mentioned voltage over the capacitor C. So VC as a function of time. Here we can add the time. Here we can include the time. It is a function of time. It should be the peak, the magnitude, which is 10, and it's gonna be the cosine. The omega, it is 1000 t. This is the omega as already given on the top there, and the angle is negative 180. This is gonna give us the voltage in the steady state domain or in the time domain. This is the voltage over capacitor C as the capacitor as required. Make sense? Then also it was required to plot these 3 phasors into the Phasor diagram as we just explained, or what we did here for the previous example, for this one. But you're gonna plot these things for the current, the 3 currents, I1, I2, and IS. Make sense? So that's it for this video. We explained the method, and that's it for the chapter 5. This is gonna be the general procedure. Your objective is just to practice more examples and more exercises on doing these impedance things and converting from the time domain to the frequency domain and practice these analysis of the electrical circuit. In terms of the part which is related to the analysis of the electrical circuit, nothing new over what we mentioned or we covered through chapter 2. You can apply any method, whatever it is, but the challenge is how to convert from the time domain to the frequency domain, and also how you can do the calculation, the summation, the subtraction, the division, multiplication of the phasors or the complex number over the impedance, then how you can convert from phasor to frequency domain or from to time or sinusoidal form, or vice versa. So these things you have to practice these things, and this is it for this chapter. And the next chapter we're gonna move to, or the next meeting we're gonna move to a new topic related to this course. All right, so that's it, and thank you for today, and see you in the next video. Thank you.